Hi, welcome to section 2.3. This section is kind of about how to take the derivative and use it to figure out what the original function would look like. So to do that, I'm going to start with an original function. I'll just draw something weird here. So I've got a y-axis and an x-axis. And then my function's going to look like that. So one thing to notice is that there's a maximum here and, well, a relative. So, and at this maximum here, the slope is horizontal, it's 0. And down here also, the slope is horizontal. So that's one clue. When we look at pictures, we can see that at the maximum or the minimum, the slope is 0. So basically, we're going to flip that concept and say that if the derivative is equal to 0 somewhere, that might be a minimum or a maximum. So let's read the notes here. Hopefully what I've drawn clarifies that. So we're going to talk about critical numbers, which is where the derivative is equal to 0. So that would be where, you've got a horizontal slope. So if the derivative is equal to 0 or the derivative doesn't exist, those x values are called critical numbers. And they're critical because we know that they relate to mins and maxes. So this second line here says, a critical number is a value of x for which the function is defined, and the function's derivative at that x is either 0 or undefined. So you take the derivative, figure out where it's not defined, or figure out where it's equal to 0, and that is probably, or possibly, a relative minimum or maximum. So that's pretty cool. So the next thing that we're going to talk about is a little bit weird. So basically, let's say I'm going to draw a picture before we read it. Say we have, like, right here at x equals 2, and over here at x equals 17. So let's assume that x equals 2 and x equals 17 correspond to a critical number. So we're going to assume that this critical number then has a flat derivative. The derivative is equal to 0. So it looks like something like that at x equals 2. And then let's say over here also something x equals 17 has a flat or a slope of 0. So, and assume that there's no other critical points in between 2 and 17. You have to assume that. So in order for me to get from 2 to 17, let's see, I'm going to draw a couple different lines here. So if I go like that, that can't be right because I'd have a critical point here and a critical point here. So take a second and make sure that makes sense to you, that that can't work. Oops, I'm trying to erase. So I've got to do it a different way. So I've got something that's continuous, and I've got a value at 2 that corresponds to a flat slope, and a value at 17 that corresponds to a flat slope. And I basically can't change direction. Like I can't go down, otherwise I'm causing there to be, a slope of 0. So my only option is to go up to 17. So I've got to make it flatten out like that. So this is a weird concept. So I'm drawing a picture. Now I'm going to read what it says, and hopefully this reading will clarify. For f of x, a differentiable function where a is less than c, which is less than b. Okay, so I'll draw a picture here. There's an a here and a b here, and somewhere in the middle is a c value. And a and b are critical numbers. And for right now, we're going to assume the only critical numbers. Okay, so a and b are critical numbers, which means somehow the slope is weird. And in fact, for visual purposes, we're going to assume that the slope is 0, because that's one of the ways to be a critical number. So if f prime of c is greater than 0, so if the slope is positive, so we're going to go at c, the slope is positive. So if the slope of C is positive for some C in between A and B, then then the original function is increasing for all the C's that are in between A and B. So basically, if you've got a horizontal slope here and a horizontal slope here, they're critical points, and somewhere on that interval there's a positive slope, then it has to be positive the whole time. So it's if you can find an example in between A and B where it's increasing, then it's increasing on that whole interval. So another possibility would be, let's say got an A and B, and again they're critical numbers, so we'll say horizontal slopes. And if you find a value like in the middle here, like a C, and at that value you discover that the slope is negative, then it has to be negative on that whole slope. It has to be negative the whole time. And then if you find, in between A and B, if there's something in the middle and it's flat at that point, then it had to be flat on the whole entire interval. So let me read all of this again. So if you take the derivative and you plug in C and it's greater than 0, and it's just some C that's in between A and B, then the function is going to be increasing on that entire interval. So second thing, if you take the derivative, you plug in C and it's less than 0 for just some C, any C, you can pick any C in between A and B, then it has to be the case that the function is decreasing the whole time in between A and B. And then if you take a point in between A and B and you plug it into the derivative, and you get that the derivative is 0 at that point, then it has to be that it's constant between A and B. So it's a little weird, but the reason we're doing this comes down to this. So if A of x has critical numbers at x equals 2 and x equals 7, then the numbers we're going to use to check if it's increasing, decreasing, or horizontal is just a number in between 2 and 7. So I can check at 3 or 4 or 5. So, and again, we're going to assume those are the only critical numbers. Let's try number 2. If A of x has the following derivatives, is it increasing, decreasing, or horizontal on the interval from 2 to 7? Okay, so at x equals 2, we've got a critical point. And at x equals 7, we've also got a critical point. So -1, it's not in the right interval. -1 is not between 2 and 7. So we're going to ignore that one. But x equals 5 is between 2 and 7. So since the derivative in between 2 and 7 is less than 0, we know it's decreasing on that interval. Okay, so the way we're going to use critical numbers is we're going to start by taking a derivative and then finding the critical numbers. And I have a mistake here. Find all critical numbers for the function by solving f prime of x equals 0. But we also need and looking to see where it's undefined. Where it's undefined. And then once I have all of those critical points, I'm going to order them so that you'll have the smallest on the left and the largest on the right. And then in between each one of these critical points, I'll check to see if it's positive or negative. And then so the point I'm trying to make up here is that if you have two critical points and there's no critical point in between them, then that whole interval has to be increasing or that whole interval has to be decreasing or 0 the whole time. So let's stop there because this is very dense. Please ask questions on the discussion board.